All right, this is exercise 5.5-12. This is page 254. Yeah, I apologize for not putting the 5.5-5 video in the playlist. I thought I had. So. That was just for giving you another example, like what we did last time. So make sure that we're all. Like I said, I also did that problem a little quickly at the end of class, so I was making sure that you had another example. Turned out that was a good fortuitous because I'd already had recorded it ahead of time, as because I was going to put it on there as another example for you, and then turned out it was a good time to put it up there since I had gone a little quick. All right, so in 5.5-12, they give you an x and a y and how they're distributed. It actually gives you the standard deviations in the problem, which is why I changed them to the variances by putting the squareds up there. Because remember, when we describe the distribution for a normal distribution, we typically describe it as the mean and the variance in that notation. So that's why those squareds are there. All right, so for part A, it asks for what are the means and the variances for the distribution of the sample means. So this is, again, doing this just as a little bit more review from the stuff that we talked about last semester. And I'm going to give you an excuse to show you something on Excel here in a second. All right, so we're given the distribution of x and y. It wants the distribution of x bar and y bar. Oh, and I guess I need to tell you that was a random sample of 8. That might be helpful. My apologies. Well, regardless of the type of distribution, if we're doing a random sample of the individual distributions, what is the mean of the sample means going to be? Just in general. Doesn't matter what type of distribution we have. What is the mean of the sample means the same as always? The mean of the population, right? So the mean of the sample means here will be 24.5, and the mean of the sample means for y will be 21.3. Right? And then again, regardless of type of distribution, what do you do with the variances when you start doing samples for the sample mean? Divided by the sample size, right? So each of these will get divided by 8. Whatever those numbers turn out to be. I don't really care what they are at this particular second. That all look familiar? No? Remember the variance thing? So, so just in general, your mean of your sample means is the same as the mean of the population, and the variance of your sample means is the variance of the population divided by n. Generally. That was our central limit theorem.
Oh, okay.
Ooh, hey, that's a mess. Yeah. But I just wanted to review it. Yes, Grace?
Why is it that yesterday, when we found the expected value of the sample variance, that it was just the variance?
Why is it? I thought I went through it.
But why isn't it the same as this?
Because I'm not doing sample variance of x here.
Then what is that?
This is the actual variance of the distribution. Right? This is the variance of the distribution of the sample means. We said that the expected value of the variance of the sample is the same as the expected value of the variance of the population. right? This is different. This isn't the variance of the sample. This is the variance of the sample means. When we're doing S squared, we're not doing the variance. That's not the variance of sample means.
So would this be like if you took a bunch of samples and then average the means? This is the variance of like
Of the means, right? Yeah. Okay. So if you take a bunch of samples, take all their means, and look at the variance of the means. That's what this is.
Gotcha.
Yeah. Whereas the S squared is the individual.
Gotcha.
Well, good. All right. So, and then of course the last part of the last part of the central limit theorem says that independent of what type of distribution it is, the bigger n gets, the closer that this gets to a normal distribution. Right? Okay. All right. So in this case, I'm assuming that x and y are normal. If I assume x and y are normal, what kind of distribution does x bar and y bar have? They're also normal, right? So just to write this down, xy being normal implies that our x bar and our y bar are normal here. That has nothing to do with the central limit theorem, by the way. That's
If and only if.
I'm not going to say it's if and only if, because I can see where there might be some strange distributions where you have, even though you're doing random samples, they're not all coming from the same distribution. I'm not willing to say if and only if without thinking about it some more. I'm certain you can make a scenario where it is if and only if, but I wouldn't say necessarily in general all the time without having to think about it. All right. But for central limit theorem, again, this says that in general, if n is large, then x bar is approximately normal. Yeah. Yep. Good. Okay. So then the last part, well, actually part B in this particular problem said that what's the distribution of x bar minus y bar then? We're assuming that x bar and y bar are normal. What will the distribution of x bar minus y bar be? Normal? What do you do with the means? Subtract them, good. So we'll take the 24.5a. So you'll subtract the means, right? What do you do with the variances? Add them, good. And I didn't simplify any arithmetic, so that's why I'm putting it inside the parentheses. So x normal, y normal means that each of x bar and y bar will be normal. So the difference it will be normal. The way we find the mean of the difference is just the difference of the means. The way we find the variance of the difference is we actually add the differences, assuming that they're independent. If they weren't independent, what would be on the other at the end here?
-2.
Yeah, minus 2 times the covariance. Well, yeah, it'd be minus 2 times the covariance. In this case, it's the difference. Right? Remember in general that if you have the variance of ax plus by, that's a squared variance of x plus b squared variance of y plus 2ab covariance of xy. Again, trying to cover a little bit of new stuff and cover a little bit of review at the same time. So you always add variances. And the reason for that is because you're squaring the negative. So you'd be squaring that negative in the middle. And again, since they're independent, the covariance is 0. Does covariance 0 guarantee that they're independent? No. Good. I remember stuff from last semester. Makes me happy. Well, Michael doesn't, but the rest of you remember stuff from last semester. Gee, Grace!
Watching at him.
Wow! Well, I think I would have actually might have caught it, but holy cow!
Sorry, last time I was way short. That's my fault.
That was. Yeah, my reflexes aren't great anyway.
Sorry.
That was.
I didn't know she was throwing it, so I didn't.
You see an eraser coming through the sky.
It's a bird, it's a plane.
No, it's just an eraser.
It's just an eraser. It's fine. Yeah, Sam.
The problem saying they were independent, or was it?
It says that they are independent. Especially since we have random samples of everything. All right. So then in part C, it asks us to find the approximate. Well, it says approximate probability, which of course is what we're going to find anyway. What's the probability that x bar is greater than y bar? So in this case, since we know what the distribution of x bar minus y bar is, what do you think we should do first before we do anything else?
Y bar.
Yeah, let's move the y bar to the other side. Right? And if we're going to do these probabilities, especially if we're using a normal distribution table, what do I need to do in order to be able to figure this out? Okay, we can take a complement if you like. We can do that first. What else do I need to do? Yeah, make it what kind of normal? Standard normal. So we'll need to subtract, what is that, 3.2? The difference of the means, right? Is that 3.2? And then divide by what? Right? Now I'd calculate. Oops, what did I do? I forgot to do it on the right-hand side, didn't I? Sorry, forgot to do it on both sides. No, it's not. I was thinking about what I was going to do in Excel here in a second, and forgot to do it on both sides. So what happens when your brain's doing two things at once? Or at least what happens when my brain's doing two things at once? It doesn't do either one well. All right. So then this is just 1 minus phi of whatever this number is, right? At this point, because we've converted it to standard normal. So it's phi, 1 minus the phi of whatever that is. So just to show you how to do that on Excel real quick. See if I can get into Excel without too much difficulty. I'm just going to show you one command, so you might be able to write it down later on in the semester. Computer for certain. What's that? Oh, okay. All right. So if I can zoom in a little bit here. I forget to do that a lot. All right, so if I start typing just equals and then start typing normal, the list of different things with the normal distribution pops up. So all the ones that have the little exclamation points next to them are the old Excel edition of the formulas. The one that we're going to want is the top one, the normal distribution, the norm.dist one for this particular case. So if I just hit tab on that, the format of it is that you want to put in whatever the x value. Notice in this case we don't actually have to standardize it either. The norm S-diff, I think, is the standard normal. So if you've already standardized it, you can just use that one. But in this one, we only had to standardize it to start with. So we wrote down the standard, we did the standard normal distribution in the previous one if we're going to do it with a table. But for this, we wouldn't even have to bother doing that. The first thing we put in is whatever the x value is that we want to be less than. The mean, whatever the mean of the distribution is, whatever the standard deviation of the distribution is, and then whether or not you are plugging it into the PDF or you actually want a probability, which we're never just going to plug it into the PDF, so that's always going to be true for that particular one. So to just show you how it works without standardizing it, the value that we had on the right-hand side there was 0, right? Okay. And then the mean was, what did we say, 3.2? And the standard deviation was the square root. So the command for square root in Excel is sqrt. And that was, what was it?
7.165.
Or it was 3.8 squared divided by 8. Was it 2.7 squared divided by 8? You said it so fast I didn't even hear what you said except for 10 point something, and then it was. I haven't done anything yet. Okay, I haven't hit enter yet. Okay, so this was the value that we wanted to be less than or equal to. This was the mean. This is the standard deviation. I had to do the square root for the variance, right? For the square root of the variance. Another comma, and then true or false. So again, if you put in false, it's going to put it into the PDF, which isn't going to do you any good for the probability, right? So we just want true here, and then finish it off. Is that the probability? No, because this cumulative goes from negative infinity up to a certain point, right? So we would need 1 minus this, which I could have done at the beginning, right? I could have gone back in here and put a 1 minus in. That way. Question, Sam?
How come when you did the true or false thing instead of false for EMF? That just standard.
I think whoever programmed Excel just used the same name for both the discrete versus the continuous. So I don't know why it says probability mass function, since it should be density in this case, because there is no point mass at any given point for the normal distribution. But, yeah, wasn't.
So we did the 1 minus because we had to do the complement in the function?
Yeah,
Okay.
that's right. Yep. We okay with that? And this probability, I don't think, is that far off of what you would expect. I mean, certainly it doesn't go against any intuition. Because think about, especially if you think about what the standard deviation is. If I actually calculate it, if I do the standard deviation of the difference here, just to illustrate what I'm talking about. There's the standard deviation of the difference, right? The 1.64. So remember the difference of the means was 3.2. 2 standard deviations is about what? 3.3? So for X bar, the sample mean to actually be less, for X, to actually be less than the sample mean for Y, that's almost a 2 standard deviation, or almost at least a 2 standard deviation difference, right? Which is not very likely. So we would expect that X bar, the sample mean, should be bigger than the sample mean for the Y's generally. So the 0.97 makes sense with what we're seeing in the problem, given what the difference of the means is for the difference of the population means is, and what the standard deviation should be for the difference of the means. Does that make sense? I didn't say it very well, but does it make sense what I'm saying? That given that the standard deviation is only 1.65, 2 standard deviations away would be 3.3. The difference of the means is 3.2. right? X bars, the mean of the X bars, the mean of the sample means is for X is on average 3.2 higher than the mean of the sample means for Y. So for the mean of the sample means of X to be actually less would be a rare event. Right? Because that would have to be almost 2 standard deviations away from the middle. That's what I'm trying to say. Not very eloquently, but that's what I'm trying to say. That's right. Math is more easy. That's right. All right. Yeah, Sam.
For bell curves, I thought 2 standard deviations 95%.
We're only on one side in this case. Right? We're only looking for a greater than instead of the less than. So it would be in between the two. So when we're just looking at one side, there's 2.5 on each side. Otherwise, it's about 97.5. You're right. For bell curves, within 2 standard deviations is about 95. But we're not worried about within. We're worried about being greater than. Yeah, greater than the -2, I guess is what you're saying in that case. All right. So let's look at briefly about the t distribution, because that's the next one that's going to pop up. F will pop up later, so I'll go back and review F. But t is going to pop up relatively soon in the next chapter. So I want to look at a couple of things. The first thing I want to look at is just how you recognize a t distribution from a particular one. And then we'll talk about how we can use it with Excel, because mainly I didn't make a copy of the t table and show you how to use the t table, but I'm more interested in the Excel anyway. So let's look at the 5.5-21. We have 3 standard normal distributions. Z1, Z2, Z3. They're independent and they're standard normal. The problem asks you for W, if you let W be Z1 divided by the square root of Z2 squared plus Z3 squared over 2, what's its distribution? It also asks you something for part B. I'm only interested in part A for this particular one. If you've looked at the text at all, they give you the PDFs for the t distribution and the f distribution. They're not pretty, which is why I'm not going to make you try to memorize them, because you'll never ever use them. Ever. Okay. You'll always go to a table or a computer to do it with the calculations, so you'll never ever use the PDFs of those things. Which is why I'm not going to make you memorize them. All right. So let's figure out what kind of distribution this has. So we've got a quotient. Remember, the t and the f distribution were both quotient distributions, right? Quotients are 2 random variables, independent. The top, in this case, is standard normal. They tell you this, right? What's the distribution of z2 squared? It's chi-squared in how many degrees of freedom? 1. So this one is also chi-squared of 1. They're independent. So when I add them together, we get chi-squared of 2, right? Now we're dividing by that 2, right? Okay. So this is standard normal on top divided by chi-squared with its degrees of freedom being divided out on bottom. So what kind of distribution does that relate to? That's the t, right? So remember, our t was standard normal on top, chi-squared divided out by its degree of freedom on bottom, and the square root of it. The idea behind this, again, and how this is going to tie in the next couple of in a couple of sections, not in the next couple of sections, in a couple of sections, is this idea of z-score again. What we just did in the previous problem, right? What did we do in the previous problem? We standardized things, right? We subtracted off the mean and divided by its standard deviation. When we're doing things with samples, remember your sample variance. If you multiply it by n minus 1 and divide by the variance of the population, you get a chi-squared variable, right? The n minus 1 s squared over sigma squared is chi-squared of n minus 1, right? So when we're doing this calculation, we're doing a z-score, except that in the smaller sample ideas, we may or may not know it's normal. So we use the t distribution. Remember I had in the video, they had a wider variance? In fact, in one of the other problems in the book, they ask you to show what the variance of the t distribution is, given the number of degrees of freedom. So in this case, this is a t distribution. And we use a little t, even though we use the capital T for the letter, we use a little t to denote the distribution. And then we also talk about how many degrees of freedom there are for the t. The degrees of freedom for the t is the same as the degrees of freedom for the chi-squared that's in the denominator. We denote it as a lowercase t, yes. And that's actually fairly standard as well. Even though we use the we typically use capital letters to denote the random variable for the distribution, but this is just a notation for what the distribution is, so we typically use a little t. And the reason for that is that when you calculate your, what would be a t-score as opposed to a z-score, but in the exact same way, we use a little letter to denote that. We're coming up with a number rather than a variable representing a function.
Yeah, so I see like how we're like dividing by standard deviation, but like for the z-score you subtract.
Right, so that doesn't have to happen up here because it was standard normal. It would be a 0 on the end.
Okay.
All right. So there is a table in the back of your book. I'm not going to go through the table right now because I just want to show you, well, mainly because I forgot to make a copy and put it on the computer because that's who I am. But there's a table in the back that looks kind of like, and it works almost exactly like the chi-squared table. Okay. So it has different degrees of, it has rows for the different degrees of freedom. And then across the columns, it has different probabilities. It has those numbers that pop up for basically what we call them critical numbers in those cases. It looks just like what it does for it works exactly like the chi-squared table does. It's just for the t distribution instead. We'll talk more about that when we actually start using it. I do want to show you how to use the computer to get some of these values as well, much like what we just did for the normal distribution. So this is 5.5-19. We have that the random variable capital T is a t distribution with 17 degrees of freedom. Part A asks you to find this. T sub 0.01 of 17. So what this means, and again I told you it works just like the chi-squared table, okay? Except that it's a different distribution. So your t distribution looks a lot like your normal distribution. That doesn't quite look normal, but that's okay. Pretend like it's a normal distribution.
Don't worry, mine was done for this.
It's hard to draw. Drawing's hard. All right. So remember that the subscript here is telling you what's in the tail, right? If I remember correctly. Make sure they don't change it up on me on the table. I'm just double checking, make sure they didn't change it from table to table. I can see that happening. So when you have t sub 0.01 of 17, what it means is that this part right here in this tail, that probability is 0.01. That's how it worked with the chi-squared as well, right? The subscript was the right tail probability. That's how the chi-squared table works too. Now, I could go to the table and read this off, which is what the practice is in the book, which again, it's not hard. It's the exact same way you wrote it off for chi-squared. Okay? But you can also get this out of Excel. So let me show you how to do that just real quick. The reason why I'm showing you how to do this in Excel is because the table, remember your chi-squared table is limited, right? You can only find certain probabilities in there. You can, whatever's in that table is all you can find. But there's other probabilities that are associated with it, you're out of luck. Right? But with Excel, you can get in other programs like R or GeoGebra or whatever else, SPSS, SAS, there's all sorts of different programs. You can get different t-values depending on what you need rather than having to be reliant on a table. All right, so if I just start to type t, there's lots of functions that Excel has with the letter t to start them. The ones at the bottom we're not interested in because we're doing these. Jesus, that's shaking. All right, so this is these first ones. It's really annoying. These first ones here.
Oh, Joe, I stopped the progress.
These first ones here are for finding probabilities associated with a particular t-value. Right? These other ones are finding a t-value that gives you a particular probability. It's the inverse, right? If we plug in a number, we get out. What we did in the previous one with the normal distribution was we plugged in a value and we got out a probability, right? In this case, we want to plug in a probability and get out a value. We want the t-value. We want that on the picture that I drew. We want that. We want whatever this value is here on the x-axis. That's what we're looking for. So we're given a probability. We want this value. Okay. So go back over to Excel. There's a couple of ways that we can do that. And it's these two here, the t dot inverse or the t dot inverse dot 2t. And you have to make a decision on which one you want. So think about why it might be called 2t. So what we're thinking about is the tail, right? That's what the T stands for. So the two tail would be, is it in one of the two tails or is it just on one tail? So the T dot inverse, T dot I and D is with one tail, T dot I and D dot 2t is two tails, which means the probability would be divided in half along each tail, right? So in this case, all we're looking for is the one tail. And we're going to do more of this as we go along. I just want to give you an introduction to it. Oops, I forgot to tab instead of enter. There we go. All right, so notice that the syntax is plug in the probability and plug in the degrees of freedom. Right? Right? So in this case, the probability, we have to be careful because it's going to be cumulative here, and we want right tail, right? So instead of 0.01, what do I want to put in here? I better put in the 0.99, right? Actually, if I put in 0.01, I would be able to figure it out. I'll show you why in a second. Degrees of freedom is 17, because that's what they told us it was. So we get 2.566 times 7.
So that's like table, ideally, it would be like in it.
Yeah, it'll be in there. Yeah. So actually, yeah, if you look in the book at the table, if you go down the T.01 column and go to the 17 row, you get 2.567. Yeah, that's actually in there. So the idea here is that if I want a different value, say I wanted the t value associated with a 73% probability, that's not in the table, and say 21 degrees of freedom, then it'll come up with a different number. Oh, I put points. I put 0.73 and 21. I was just making up numbers. Yeah, Megan.
Can you explain one more time why you did the minus 0.01?
Because the 0.01 refers to the right tail probability, and that t dot inverse command is a cumulative probability, so it's a left tail probability. So I had to do 1 minus to do the left tail. That was why. However, if I hadn't remembered to do that, so let's say I forgot, because I'm not very bright, then I forget. Okay. Which I'm not very bright, so I forget. So say I put 0.01, notice it just gives you the negative. It's because it's symmetric. The t is symmetric. You would just need to remember that, oh, hey, I goofed up. I really meant the right tail, so I'd have to delete off the negative. So even if you forgot to do the complement, you still should be able to get the right answer. Because that negative should say, hey, wait a minute, that's over here on the right. What does it mean? It's giving us, instead of plugging in an x value, essentially, and getting out a probability, it's working backwards. So for what we're going to be doing later, when we want to know probabilities of being wrong, for example, and then figuring out a critical value of making sure that if I'm above this level, I have a low probability of being wrong. That's what this value is giving us. It's those cutoffs. So I'm willing to say that I'm confident that I'm not wrong above this particular value. And I don't want to go into more than that right now because we're going to talk about it more later. But that's what it's representing. It's doing the inverse problem, basically.
Is that one of them just go like up and
Yeah. All right. You okay with that? What's this in? Shy? No. No. All right. Is this okay with this? If it were a two-tail, notice I would have done the two-tail probability instead, just to show you real quick. So say I did the dot 2t instead of the dot 1t. If I would have done 0.01 here and 17 degrees of freedom, it would have given me a higher number because it's taking that 0.01 and splitting it into the two tails. So there's a 0.005 on one and a 0.005 on the other. That's why the number is bigger. If I did t dot, equals.
would that be plus or minus though?
Yeah, that's exactly right. There would be a plus 2.89 and a minus 2.89. Yes. It's not doubling the t value, it's doubling the probability. So notice if I did 0.995 in that case. So if I have the probability, I'm just on that other piece. So what I mean by that is over here, whew, oh, you get the idea. Lay off me.
It needs wheels. You give it wheels.
Little puffs of smoke coming out the back.
Oh, this is perfect.
Is that better? Okay. Anyway, if I was looking at the two tails, what we're doing here is we're saying that these have been split into two. And so there's a 0.005 here. But I didn't have to move very far to get to cut the probability in half. So that's why it's not doubling the t value. Does that make sense?
Shake my leg. So I think it's me that's shaking it. It's really weird.
If that's you, that would be really weird.
I know, it's not.
All right.
It just like makes me stop moving.
All right. One more quick little thing I want to talk about, and that is section 5.7. I'm not going to talk a lot about 5.7. Five 5.7 is approximations for discrete distributions. And the idea here is that, well, before the advent of computers and calculators that could do these things and not have to worry about lots of computational overhead, the idea is that some of these distributions that are discrete are hard to calculate the probabilities for if you're doing it for lots of possibilities. For example, if you wanted the probability, say you had a binomial experiment and there were 50 trials and you wanted to know the probability that you had 24 to 47 successes. That's a lot of computations, right? Right? So what you can do instead, if you have the right setups, what you can do instead is use the normal distribution to approximate. So for the normal distribution, you need to know the mean and the variance, right? Well, if you have a binomial distribution, if x is binomial on n and p, what's the mean and what's the variance? Cool, good. Okay. So we know that if x is binomial on n trials and the probability of success p, then we know that the np and the np times 1 minus p are your mean and your variance, right? Now, if you do this for several different n's and p's, which I'm not going to go do because of time, I could do this on GeoGebra that makes nice pictures, but if you have big N, for example, that's going to make this value be a whole or a bigger number, something that's relatively large, and it'll make this one relatively large too if N's big enough. So you're doing a large number of trials, right? And in particular, a rule of thumb is that if your N times P and your N times 1 minus P are bigger than 5, then this really looks bell-shaped. It looks like a normal distribution. Okay? So, and if you just look at some histograms, you can look at that pretty quickly. So if NP and N times 1 minus P are greater than or equal to 5, then the distribution is bell-shaped. And in that case, if it's bell-shaped, we can use a normal distribution to approximate. What do you think we would use for the mean and variance to approximate? What mean and variance for the normal do you think we would use to approximate? Yeah, these and this n and this mu and this sigma squared, right? We would just use that mean and that variance. Yeah, Grace.
Why is it untitled?
It's just a rule of thumb. It's to make sure that your probability of success and your probability of failure isn't skewing things. So if your probability of success is really, really high, you're going to get a distribution that's really skewed to the right. Okay? But that means that your probability of failure is really, really low. It's basically a measure of how it skews. So if P is really, really high, I mean, it's something skewed this way. But if P is really, really high, then 1 minus P is really, really low. So you need a really, really large N to counteract that skew. And then likewise, if P is really, really low, then you're going to get a skew like this. And then again, so if this is low, you need a really, really high N to counteract that skew. That's the idea. It's a rule of thumb. Sometimes it needs, if it's really, really, really small, you sometimes want an N that's even really, really bigger to make it bigger than 5. Yes?
So what if N is like 300 and E is 0.9? So it's like super.
Well, if your P is 0.9, then it's not. It's if your N is bigger, then you're fine. It won't be that skewed. Because if you actually look at the distribution, it won't be that skewed in that case. But if your n's are small, then it'll be really skewed. So are able to get the approximation a little bit easier that way. Anyway, I don't really have time to do an example, so we'll do an example at the beginning of the class next time. You can do the same thing with the Poisson, for example. If you know a Poisson, if you know the lambda, then you know the mean and the variance. And if your distribution, if your lambda is a decent value, then it'll also be semi-bell shaped, and you can use the normal distribution to approximate that as well. I will post a video on YouTube for you to watch for Monday as well. It'll cover 6.1. Have a good weekend, everybody. I didn't let you out late.
Made up for the lateness.
I'm really going to try to remember because I know that several of you have to go over to Scoville. Yeah.
We need Haley in the back.
What was the
Or we just make your science.
Yes.
Yeah.
Do you think Dr. Roth will let me read classes?
I don't know why he wouldn't, but I mean, just ask him and let him know why.
Yeah. Because like we have to leave at 1 to get to the conference, right?
Yeah, just let him know. I'm sure he'll be fine with it.
I didn't know if he was like a super strict teacher.
No. If you let him know ahead of time.